So then we come to another type of magnetoresistance. This is probably the most recent. Most recent, I mean, means it's been around for maybe 5-10 years. But I think commercial applications only came about
some years
back. It's called tunneling magnetoresistance.
Okay.
Okay. I think we now this is the third magnetoresistance type we're talking about, correct?
Talked about AMR, GMR,
TMR.
GMR itself, spin valve is a subclass probably.
Yes, but I think nowadays people mostly use spin valve type sensor
because they are
for most applications, right? Because of that nice linearity.
Yeah.
And then you don't need huge magnetic fields.
Yeah.
Right. And especially if you're talking about small devices, it's hard to get strong magnetic fields to change direction.
Correct.
The magnetizations, right? So, yeah. So it's more practical to use that spin valve type GMR sensor. So the tunneling magnetoresistance sensor is actually very similar. Here, again, you have...
I can see 3 layers again.
Yeah. In fact, there's also a 4th layer, the antiferromagnetic layer. But I haven't drawn it here. By the way, another way to pin this is to also have, let's say, a bias magnet.
Okay.
Right? But the smaller your device gets, the harder it is to have this bias magnet.
Yeah.
Okay. But here, so it's the same setup.
Oh.
The only difference is, instead of this nanomagnetic conductive layer that we saw before,
you have an insulator.
We have an insulator. Exactly. So we have an insulator.
Then how there will be current flow?
Insulator, like let's say oxide or some of the common ones that we use. Now there are 2 differences. That's the first difference. The second difference, and this will answer part of your question, is that the current, generally for spin valves, you apply the current this way. So your scatters and comes out, right? So I is here and comes out here. Okay. Now, here, I'll give you a clue why we have this. Your current is applied perpendicularly, this way.
Also, for the other one, current is the current flow is in...
Mostly. For most applications, current flow is in the in-plane direction. Not for all applications, but for most applications, it's in an in-plane direction. Because if you look at a little chip, right, it's easier to apply current in planar rather than from the top. And I will come to that. But so here, current is applied perpendicularly, right? In this case, your electrons, same electrons we talked about before.
Yeah, to love to jump.
Yes, it doesn't jump. What this does is it tunnels through this insulation layer. So this actually
so it's a very
thin layer and acts as a tunneling barrier. So electrons are, instead of scattering, they are tunneling.
Okay.
Right? And that's why we have this name,
tunneling
magnetoresistance. Again, same principle. When the magnetizations are parallel, your resistance is low. When the magnetizations are anti-parallel, the resistance is high. Okay, same principle. Now, and you can think of it in the same way. When your electrons are now tunneling, not scattering, when they're parallel, there are more majority electrons that are tunneling through this layer. When they're anti-parallel, the probability of these minority and majority electrons to tunnel through reduces. So you get a high resistance.
Earlier we were mentioning spinning, etc.
Yes.
So this upspin electron can move from bottom layer to the top layer only if there is a upspin electron vacancy at the top layer.
So you're talking about GMR?
No, tunneling.
Tunneling, yes.
Only if there is a vacancy, it can jump by, or it can tunnel through.
Yes, you can adjust otherwise tunnel through, right? Yeah. So the ferromagnetic layer has some.
Yeah. So the external magnetic field that we apply,
yes,
can generate upspin or downspin electrons depending on the direction of the external magnetic field. Am I correct?
Depending on the magnetization, you mean?
Yeah.
Yes.
I mean, it is already magnetized as you are drawn.
Yes.
Correct?
Yes.
Now
It
if
can change. I mean, this
Yeah.
cannot change,
Yeah.
but one can
Yeah.
free to move.
so now if I bring some external magnetic field, the layer magnetization can change.
Yes, in one layer. Not on both. Not
Yeah.
in both layers.
Yeah.
Yes.
So which means if it is only upspin,
Mhm.
then if I am bringing external magnetic field, I can have some downspin also there.
Yes. Yes.
Hmm.
Technically, yes.
Yeah.
I think so. Yes. I guess so. Yeah. I mean that makes sense to me. Yeah. Yeah. So basically, I mean, you can just think of it as a tunnel like this, right?
Yeah.
And you see you have upspin and downspin electrons. I mean, if you have a current, you have both, right? Generally, in a current.
Yes.
Yeah. So now, how many tunnels through depends on if the magnetization are parallel or anti-parallel.
Yeah.
Right. So in this case, you can see both upspin and downspin going through, and that means that it's anti-parallel.
Correct.
Right. Again, the graph looks very similar, right, to the GMR. Right. You have the linearity here. Again, you fix it in a perpendicular direction, the free and pin layers, and you get this kind of graph. Now, Bobby, TMR sensors are more sensitive and use less power than AMR and GMR sensors. But what do you think are some of the challenges with TMR? Why do you think it took a long time for TMR to become, let's say, commercially available and commercially successful, rather?
Maybe there is some fabrication challenge.
Yes, one is one reason.
The insulator there.
Yes, so that means this because this is an insulator. So and also it has to be a very thin insulator. So first of all, you have a fabrication challenge there. Plus, this insulator should also be pinhole free, right? If you have some small holes, then they're going to tunnel through regardless of your magnetization.
Correct.
So from a fabrication point of view, it's quite challenging. There was also a lot of noise in TMRs compared to AMR and GMR, but people have worked through that. To now we have very, very good TMRs. In fact, TMR, I believe, has overtaken GMR spin valves in most applications now. But GMR was the original,
Giant
commercial,
Magnetoresistance. Yes.
commercially also very successful, right? Used in a lot of applications for a long period of time. The third problem was, or the challenge rather, was current is applied from the top.
Yeah.
Which means if you're applying current, you'll have to have, let's say, two wires, for example, and top and then bottom. Again, from a fabrication point of view, this is difficult.
Correct.
Rather than having just a nice little thing where you can wire bond outside. So those were some of the challenges with TMR. So going forward, we'll focus on GMR because GMR has been used for a long time and we know it's been very successful. So we're going to talk about a few applications of giant magnetoresistance. Even though TMR now is probably at the forefront of these magnetoresistive technologies.
So these are commercially available to buy.
Yes. Now, and they're actually very sensitive. Very sensitive, and but people did spend a lot of time trying to solve the problems we just talked about.